Welcome to day 2 of the OARC Spring Workshop from Warsaw. For those of you who weren't here yesterday, I'm Keith Mitchell, OARC President. We have a number of talks this morning. I'd like to introduce Sean Stewart as our session chair for this morning, one of the program committee members. Before we start off, a few routine administrative announcements. First of all, I'd once again like to thank our sponsors, Microsoft and VeriSign, Platinum and Gold sponsors. Also like to thank Dine and NZRS for the social last night, which I thought was very welcome. And an additional thanks to Joe as our quizmaster, or seriously jet-lagged quizmaster. And also congratulations to Team Sexy, the victors of the quiz, and the prize for the quiz is a Xbox One, generously donated by Microsoft, so thank you, Mehmet, for arranging that. And the second prize was apparently a box of candy from ISC, and my team was second, and I have not seen the candy, so... Anyway, don't forget that we're webcasting, so make sure all your noise-making devices are switched to off. Wait for one of the microphone runners, Sean or Billy, to come and bring you a microphone and identify yourself and your affiliation before speaking. As for yesterday, the coffee break is here in the foyer. The lunch is in the kitchen gallery restaurant upstairs, for the same as restaurant as breakfast. In the event of an emergency, leave via the stairs that you came in, and there's an emergency exit to outside the hotel beside the bistro entrance, cloakroom entrance. Speakers, I think we have most of the slide decks, but if you have not uploaded your slide deck, you need to update it. Please upload it into Indico and let Sebastian and myself know. Also, please make sure you speak to your session chair before the start, and just check of any arrangements. So we're basically ready to start, so I will hand you over to Sean and our first session of the day.
Good morning. First session of the day will be William. William here, go ahead and get started.
Oops, wrong one. Sorry. Okay. Yeah. Huh? Oh yeah. Oh, sorry. Yeah. Yeah. That's it. So I am Willem Torop from NLNet Labs, and this presentation is about the GetDNS API implementation. The GetDNS API is a DNS API specification for resolving, and it's designed by and for application developers. And I've been working implementing this specification, and this was a collaborative effort of VeriSign Labs and NLNet Labs, and quite a few people involved. And Sinodon just joined the team. So why would applications want to link against a library like that? Well, there is the last mile problem. This is the normal DNS ecosystem. The validating recursive resolver in your network protects the application that is using the step against domain hijacking, because it's validating, it cannot be cache poisoned. But the application through the step does not know about this. So maybe we need something that passes the AD bit up. But that's maybe not enough, because the local network could be compromised as well, and a malicious resolver pretending to be the network resolver could then just pass answers do domain hijacking and set the AD bit himself. So what you need is a library for the application to link against, which does the validation as well. And this, if the library, DNS resolving library would do this, there is another advantage, which is that you do not need a validating network resolver anymore, because the validating stub can do all the iteration, DNSSEC iteration, walk the DNSSEC chain and do the validating for itself. And the recursive resolver just has to be DNSSEC aware, past the RR6, able to look up DS records and DNS keys. And at RIPE, there will be a session of a student project we did at NLNet Labs, measuring DNSSEC validating resolvers in RIPE Atlas network. And within RIPE Atlas network, 90% of the network resolvers is DNSSEC aware, so able to give you the DS records and gives you the RR signatures. Now, I know the RIPE Atlas network is sort of biased, but still modern resolvers should be able to do DNSSEC or fetch the records needed to do validation at the step level. So, and why would the application need DNSSEC besides the last mile, also to get authenticated entries from the DNS? Bootstrap encryption channels. Dane. Here, this cartoon is by Claude. So this is a perfect application for GetDNS API. So there were some other reasons. Some of the things are not available with get name info and get other info. It accidentally says 2 times get other info, like text records, SRV records, Dane lookups. More and more are specific for applications. So a bunch of people, Paul Hoffman led them, they started to design a DNS API specification for application to link against, because they were not happy with the DNS libraries that were already there. So they decided if we design one ourselves, then maybe someone implements it and we will be happy. And the first publication of the GetDNS API was in 2013, April. We have been working on it since September 2013. Oh, yes or no? No? Me.
Wrong answer.
Okay. Right. So this is the motivation for our implementation from our README. We like applications to be built that open encrypting channels, using DNSSEC to bootstrap that. There have been 2 releases up till now. We have Node and Python, or JavaScript and Python bindings. We spoke at IETF in London, and we organized a hack battle, which was very nice, but is not in this presentation. So those are the features of the GetDNS API. I'll have a hands-on GetDNS API later. And these are the things that we are going to address. It's a resolver, and it can be in stub mode, but it can also do full recursion. The default modus operandi is asynchronous, which was very important for the application developers. there is a response data structure which is very extensible, which we are going to look into. We're going to look into the different modus, several ways of doing DNSSEC, and have a look at the event bases. Those are the dependencies. lib unbound for resolving. LDNS parses the wire format, creates the getDNS structure. librdn only for those two functions which were part of the specification. There's a pluggable extensions for event libraries. And also, you need to have, very important, a trust anchor installed if you use the library. Otherwise, it won't be able to do DNSSEC. These are the platforms we support. Some people are making packages for it or preparing packages for it. Windows and Android are on the roadmap. So there are actually 4 function primitives in the getDNS API, and this is the mother of all the primitives, the getDNS general. There's a global configuration parameter which is called context. In context it is configured if it's in stub or full recursive mode, the timeout values, root hints, forwarders, etc. But also if you are in full recursive mode, it contains the resolver cache. These are the name and the type you want to look up. Then with extensions you can pass in several extra parameters specific for the request. For example, for address lookups we have return both v4 and v6. That's the query for address records and parallel, and returns you both the answers. DNSSEC return status gives you the DNSSEC security assertion. To look up something else than IN, you have to use the specify class extension, which we didn't implement yet, and add opt parameter for eDNS 0 records. We haven't implemented that yet, not yet either, but we will be implementing that last one very soon. The last 3 parameters are for the callback. So the default mode operandi is asynchronous. It will be, when it has found the answer, it will be calling the callback function, and it will pass in the user argument that is provided by the user. Also, a transaction ID is generated and also passed to the callback function. This is the type of the callback function. I've colored the parameters that will be passed. And there is also, of those 4 primitive functions, a synchronous version, which will return the response dictionary in the reference to a response dictionary parameter. This is the second primitive. It looks up addresses, so you do not have to specify the type and the extension return both v4 and v6. Also in the specification it states that it will look into other name systems. We have not implemented this yet. I guess we will implement the local files name system soonish. This is for reverse lookup. The input is data structure similar to what is going out of those function primitives. I will talk about it more later. And there's also a primitive for SRV lookups. This is what the response object looks like. It sort of looks like a JSON structure. You have what type of name system you've used, DNS in this case, the answer was received successfully. Apparently it was an address lookup because it has an entry just address answers. It has the full wire format packets in the replies full, and in replies 3 you have the wire format answers, but then broken out into the specific in their specific elements. Well, to represent this structure in C, the API contains a few structs, these, and a dict and a list, basically, and a bin data. And ints are also used, and a whole bunch of accessor functions to create, modify, and access those structures. And this is, in C, this is not the most intuitive way to program against a library. Here you see an example of how to look up a address and get the first answer. But in the language bindings, for example, Python and JavaScript, it's very the natural way to do things. It's Pythonic and JavaScriptic. Python bindings have been implemented by Melinda Shore. The JavaScript bindings by Neil. More bindings will follow. So it might not be intuitive in C to program against, but it's a good fit for modern scripting languages. Also, it provides a uniform grammar to of all the things, and it's extensible. The extra layer of indirection, of interpretation, makes it that you do not need to add new function prototypes if you want to add another feature. So it's more easy to extend it with new features and standards developed in the IETF, for example. On our website, there is this query page, and you can use it to do queries with our implementation, and it prints out the structure. So you can already have a look at what is returned with this library if you resolve. DNSSEC, there are 3 extensions that give you DNSSEC. The most basic one is return status. It gives you a DNSSEC security assertion. It will say with each answer in the replies tree section what the security status is. But if an answer will be bogus, it will not be included. So the security status here will never be get DNSSEC bogus. There's the extension that returns only secure answers. This is perfect for DANE type of applications, because you only want to bootstrap encryption when you are sure the answer is secure, and also all the C names towards the answer, etc. So this one will never give you the status indeterminate or insecure. And there is the extension return validation chain. This will return everything if you enable this extension, including all the answers that are bogus. Now, in the specification, you enable one of the DNSSEC options per on a query basis, and we didn't really like that. We want to have DNSSEC on by default, but it's not. So we also make our own primitive that just turns it on in the context. But this is implementation specific. Here is what the DNSSEC return validation chain returns. It returns the whole chain, all the RRs that are needed to authenticate an answer. So from the root up, all the keys, signatures, TSs with signatures, etc. There's also a function primitive that can take a chain like that and validate an answer. You have to specify with a trust anchor. we have a extensible way of hooking up event libraries. If you compile the GetDNS implementation with all the options to configure with different event libraries, it generates 3 modules. This is how lib-event works. It's in the function event-based dispatch that does all the work and executes the callbacks. Here are libev and libuv. Similar way to do things. And also we implemented a way to do it without any event library, just with normal select by getting the file descriptor from the library and waiting for reads on that. So, what's up for the future? Well, there are quite a few extensions we have not implemented yet, and some are really easy to implement, low-hanging fruit like specify class. So we'll be implementing those this soon. One that was not so easy is the add opt parameter. We currently use libunbound for full recursive and step mode, and setting eDNS 0 options is only makes sense in hop-to-hop context. So libunbound thinks that you talk to it and it does all the talking to all the different name servers. So it's not possible to set eDNS 0 options with libunbound. So we have to re-implement that in LDNS. And John and Sarah Dickerson of Synoden are going to help with that too. And we plan to have that finished before the IETF 90. More language bindings, platforms, name systems. We also would like to, still would like to have a more C-like access to the response dictionary, make it an opaque type, and change all the dictionary names into accessor functions. And yeah, optimizations. This fits well with the plans. I'm also the main programmer for LDNS. LDNS does the same as GetDNS at this moment. If it parses wire format, it builds up this data structure and then hands it over to the user. And I'm working on a way that you keep the wire format to make it more lazy. Keep the wire format as long as possible and only build or deliver you the pieces that you really want. That's my presentation. Here are all the details. How to get more information on it.
Thank you, Willem. Are there any questions? Quiet crowd this morning.
No?
All right. Thanks very much, William.
Yes.
Well, if there's no questions, may I just wonder if people in this room feel that this stuff serves a need. Just a show of hands. That's about half. Who thinks that this is a lost cause? There's no hands here. This is good information. Thank you.
Thanks. Next we have DNS Tap with Robert Edmonds.
Hello, I'm Robert Edmonds with Farsight Security. This is my DNS Tap presentation, and I'm also going to give a status update on what we've accomplished recently. So first off, here's the URL for DNS Tap, just dnstap.info. We've got links to all of the documentation, code, mailing lists. So just this one URL to remember, or you can get the slides and link to that. If you're interested in this topic, there is a low-volume mailing list linked to from the site, which I would encourage you to subscribe to. And we have the links to the GitHub repositories and downloads and all that, and the as well as the PDF slides from the various DNS tab presentations. So basically, it's protocol buffers format logging for DNS software. So within a piece of software that interacts with the DNS, we want to be able to do logging. And usually the solution here is just printf, just take some text and print it out within the name server. So usually that's not sufficient, and we have to resort to going outside of the name server doing packet capture based logging. This is sort of a middle ground between having granular binary format and having the ability to export context from within the DNS software itself. And here's a link to the protocol buffers schema file if you're familiar with protocol buffer messages and how they're encoded. If you're not familiar with protocol buffers, it's a fairly mature technology by now. It's been out for a number of years. I think Google open sourced it back in 2008, and it's been under development for a number of years. It's a pretty natural fit for encoding DNS data. It's binary clean, unlike JSON or other encoding formats where you have to base 64 encode your binary data. So we can embed binary clean data with no overhead. Has a very efficient encoding. It makes a very efficient use of the available bytes. And it's extendable in terms of being able to make backwards compatible extensions to a schema. And there are implementations available for pretty much every programming language. You have the usual C, C++, Java, Python, many Perl implementations, Ruby, Visual Basic, Erlang, Haskell, etc. So it's a very widespread technology in terms of being accessible from many different programming languages. And that here's the schema, the top level schema. We're just going to dive right into the definition. There's a top level container for all different types of DNS tap messages. We have various fields that are optional and can be set within the top level container. There's an identity field and a version field, which are sort of the DNS tap analogs of the NSID and version.bind fields that are seen in DNS server implementations. So if you have a collector that's collecting data from many DNS tap formatted data from many servers, you might want to be able to identify which server sent that payload, what version, what software was running and generated that that data. There's an extra field for being able to embed additional annotations, application-specific annotations into a particular container message, and then finally there's the this actual union type of the embedded payload. And currently you have an option of one of the following options. You have the message type, and we want to. This is basically a wire format DNS message, for instance, from a query or a response, and we want to be able to extend this union type with additional possibilities in the future. Okay, here's the message schema. This is the type that we've defined for encapsulating wire format messages. And there's exactly one field that's required, this type field that identifies the actual type of the message, and then all of the fields after that are optional and can be filled in or not. So the type field identifies both whether it's a query or a response, and it also identifies what kind of the role of the software they generated. So if you're an authoritative name server, those are the auth query and auth response types. If you are a resolver, initiating an upstream lookup, you have the resolver query, resolver response, and then there are a couple of more for stubs and forwarders, and then there's a generic tool query and tool response. So something like dig, kdig, drill, looking glasses, those types of software tools can use this particular type. So we can identify what kind of software is sending or receiving a message. And we have socket family, socket protocol, query address, query port, response address, response port. These are basic network tuple level information. So we have IP addresses of the initiator and responder, the port numbers, this type of information. This network header level information. Then we have timestamps at seconds and nanoseconds granularity. For either the query or the response or both, if you want to calculate RTTs, that kind of stuff. Then we have fields for both the query and response. So if it's a query type of message, there will be this query message field will be populated. If there's a response message, the response message field will be populated. There's also this query zone field, which I will talk about a little bit later. But the idea is that we can export information that's not directly visible solely at the network level, since we are inside the DNS software. First off, a sort of a digression into framing. There's a problem in that protobuf packs only one payload at a time, so we need a solution for packing a stream of these payloads, and the solution is very simple. We're going to just write the length of the payload, and then write the payload, and then repeat. A very simple idea there, but the problem is that we need a way to serialize these payloads continuously. Sort of like in syslog, you separate the log lines with a new line. You just send a line one after the other. So it's sort of an analogous situation there. And the implementation of this is called frame streams. Just a lightweight protocol for streaming these data frames, which are going to be protocol buffer encoded. We want to be able to stream these over a socket or read or write them to a file, so it's a both a file format and a socket protocol. Nice thing here is that we don't need to know how the data frames are encoded. We're just shuffling around these opaque binary data frames, and we have a reference implementation of this idea called fstrem in C. It's fairly easy to parse. I wrote a proof of concept decoder in Python in 50 lines with no external dependencies. So the idea here is different programming languages should be able to parse this file format very easily. So now let's go back into the use cases for DNS TAP. These are 3 different use cases that I've identified for the message, the DNS TAP message schema. We have an interchange format for tools. We have passive DNS replication, and we have query logging. These are 3 separate use cases here. First one is the interchange format. This is a pretty simple idea. You have a lot of command line tools that send and receive DNS messages. You have dig and now delve without an E, drill and kdig. You have looking glasses that it would send back the response from a remote location. And these tools all do their network level sending and receiving of these DNS messages, and then they immediately display it. You have the traditional dig style, which is reminiscent of the master file format. You have various JSON encodings, but you're all converting into some other format for display. So we have the network level send and receive, and we have the display, and they're usually embedded into this single process. And there are other obviously you can do whatever other additional HTML and text and whatnot. For instance, from the Looking Glass type utilities. But basically, for this interchange format, what we want to be able to do is save a copy of the original DNS message trace and separate the reception and the display into two different tasks and be able to decouple these tasks. So if we want to display the message trace now or later, we can do that, and we have the original verbatim wire message in order to be able to refer to instead of copying and pasting the output from one of these tools. You can preserve a more granular original format message. And for Looking Glasses, it would be nice to be able to communicate the original wire format response message rather than immediately transcoding it into some other format. So that's the interchange format use case. Now here's the second use case, passive DNS replication. This was the original use case that really motivated DNS TAP. This is usually done by packet capture, logging of the authoritative responses that are initiated by recursive resolvers, and the idea is to extract the resource records from those responses and build up a historical data store of those resource records. Problem here is that instead of capturing the responses from our PCAP tool, whatever, we are capturing the packets that contain the responses. This is kind of a subtle point, but the network level artifacts are somewhat different from the actual response messages that we're interested in. So there's a number of issues we have to take into account. UDP responses may be spoofed, so we have to verify that the response is in response to an actual outgoing query. We don't want to just accept any blind UDP response that may have occurred. We have to deal with eDNS fragmentation. That's annoying. TCP segment reassembly, also annoying. UDP checksums, etc. Those are all network level artifacts that have to be resolved before we can get at the original wire format response messages that we are interested in. There is another issue with passive DNS replication, which is this passive DNS bailiwick reconstruction problem. If you Google for this phrase, you can get a long write-up of this issue. And basically, you have to keep a large amount of state. Basically, you have to reconstruct the entire DNS delegation hierarchy and be able to place these response messages into context and be able to scrub out unintentional or intentional poison. The DNS TAP alternative for this use case is to simply log the bailiwick, and it's just a simple, copy this field into the logging payload and export it. It's pretty much the opposite in terms of difficulty. Query logging, third use case is we want to log queries that a server receives. And you can do this with packet capture, obviously. You can do this, many servers have a built-in text format, query logging format. There's additional metadata that doesn't occur at the network level that would be interesting to log. In the recursive case, you might be interested in whether your query hit a cache or if it's a cache miss. In the authoritative case, you might be interested in which zone served a particular query. These are both information that has to be, it's not directly visible from network level tracing. Here's our diagram of how a DNS TAP enabled DNS server works. We've added this stuff to the right over here and this stuff to the bottom, but basically this dotted line is the This dotted line is the inside of the name server process. It's getting DNS queries and responses from outside, from the network, processing it in its worker thread, and then it's going to generate a logging payload. And instead of writing it to a file or sending it over the network, it's going to pass it to a circular queue and defer it for later processing by this IO thread over here. And so this is our architecture for preserving as much as possible the performance of the DNS server. And then it's this IO thread is then responsible for later asynchronously writing out these logging payloads to a byte stream socket. And then we have a separate capture process which can then do whatever analysis on that on the received payloads. In this case, it's just a simple logging utility that writes it out to a file. So that's the sort of ideal architecture for a DNS tap-enabled DNS server. Obviously, there's a lot of components here. So we have these pretty much 4 different areas of the DNS tap ecosystem. We have this dnstap.pb. This is a link to the repository. This is the protocol buffers schema, which defines the log format. Then we have these helper libraries that are for adding support to existing DNS software. These are C libraries that do the framing and the encoding of the logging payloads. And we have patch sets to integrate this DNS tap support into existing DNS software. We first started working on Unbound. We've later started looking at NOT as well. We have capture tools for receiving, displaying, analyzing the logging payloads that are generated by these servers that have been had DNS tap support added to them. And finally, here's our status update. In the last few months, we've been the framing library has been under heavy development. We have a release candidate for the protocol buffer C library, which we've started maintaining after the original developer ran out of time to continue working on it. We rebased our Unbound patch set and actually went to InnoNet Labs office and presented this. Results were seemed to be positive, so we're hopeful that we can make some additional improvements, and perhaps this might appear in a future release. We've just started working on NOT and KDIG. We presented this at CZNIC Labs, and they seemed to be receptive to this sort of support as well. In fact, there's a branch in their Git repository with a sort of the beginnings of a support for this. So there's those 2 servers. We are also interested in adding support to bind, but we've not yet begun work on that server. And again, that's the here's the URL for this DNS tap project. Are there any questions?
Do you have tools to generate sample data that you can test your own tools against it?
Sample data.
That you get sample queries and responses, so you don't have to set up the whole infrastructure that you can test your software against it.
Not really. I mean, there is some examples on the website, but we don't have any sort of like an archive of sample data. So.
Thank you. Lars Lehmann from NetNote. Is there a separate collector engine that a kind of a wiretap that produces this type of output?
In our diagram here, we've shown this, the separate capture process, and this is actually a completely separate tool from the name server. Yes.
All right. So that can listen to the wire and kind of
What do you mean?
Peak packets from a mirrored stream, so to speak.
No, this is not packet capture based. This requires the name server to open a socket connection to the capture tool. So it's more like a NetFlow collector than a packet capture based tool.
Right, but what I was looking for was a separate application that only does that only listens to the packets and opens this stream to deliver the content.
No,
Okay.
that's not envisioned in this particular architecture. I mean, we've
Right.
worked on similar tools in the past, but this is more targeted at a more intrusive level of logging, which requires modifications to the software.
Oh, okay, thank you.
Kathy Almond, ISC. I'm looking at the circular queues, and this may be a naive question, but is there a risk of the DNS TAP IO thread not being able to process the data from the circular queues before they flow around on each other?
Yeah, there is that risk. It's designed to drop data if it can't keep up, rather than blocking the worker threads from making progress. So we don't want to impact the performance of the server. For PCAPs, you have a similar problem because you have a fixed amount of buffer space in the kernel, and so there's a very analogous situation there.
So you still got the potential of not capturing everything,
Yes.
but sampling instead. Okay.
George from APNIC. I had an analogous question. The PCAP driver, as I remember it, tries very hard not to get double read cost. If two people are consuming the same source, it doesn't cost that much radically more. And it occurs to me it would be nice to get something like a DSC producer out of this so that you could generate the same kind of stats, given that you've got the information passing. Have you got an engine to minimize the cost of having multiple reads on this thing?
Not really. The multiple reads would certainly be an issue outside of the name server down in the capture process if you needed to split it out into separate tools. So no, that's not something we've thought deeply about now.
What sort of performance are we seeing so far?
Performance tends to be pretty good. Compared to query logging, it does not slow down the name server as much, since there tends to be a lot of locking in query logging implementations. Generally, in the unbound patch set, which is the most mature and which I've benchmarked the most, the overhead scales fairly well. It's typically a fixed amount of overhead in terms of CPU usage, probably in the range of, if you have 3 cores being completely consumed by DNS serving, adding DNS TAP might take 4 cores. But the idea is to be more efficient than query logging.
Any other questions? Any other questions? No? Thank you, Robert. Next, we have Big Data with Sebastian.
Yeah, for a moment I thought everyone was sleeping. It doesn't seem to be the case now. So let's do a test. I have free stuff. Good. All right. All right. For those asking questions at the end of the presentation, I have some. This is from the marketing department. Sorry. We have some shirts on all sizes, M, L, XL. All right. So. Sorry, George. Australia is not by the side. There you go. Okay, we have 3 different models, so prepare your questions. I was really interested on the DNS tab presentation because one of the things, or one of the potential of big data on the DNS space is actually streaming DNS data, for example, DNS logs, into data analytics engine and start getting information out of it. You might think counters, or you might think, I don't know, number of queries for certain addresses, but actually there are some people that does very interesting stuff with DNS, for example, for detecting anomalies or detecting infected hosts. So, and because DNS tab use protocol buffers, and protocol buffers more or less integrate reasonably well with Hadoop, there might be some potential in there for streaming actually data from DNS directly into Hadoop using that protocol. So that's another idea. All right. My presentation for today is what we call the big data journey, which is precisely from a palette of parts to big data analytics. My name is Sebastian, and I work for the DNS Register Services. This is just a little bit of introduction in case you haven't heard anything about Hadoop in the last year. I have to give you a warning. There's a lot of buzzword that management loves in this presentation, like Hadoop and big data analytics. But I'm not intending to sell you anything here. We're just sharing our experience. The Apache Hadoop is a kind of a framework to do big data storage. So lots and lots of data on very cheap hardware, and also data analytics over that data. So the storage is prepared using a component called HDFS. This whole thing is Java, so it's kind of heavy, and there are some funny, interesting stories behind how to run it, Ryan and there are all kind of possibilities for doing data processing. The main concept under the Apache Hadoop environment is the MapReduce, where you have multiple tasks that will run in parallel doing mapping data and then reducing data. And then you can use the high-level tools like Pig or Hive to run queries. So in Pig, you have a specific language called Pig Latin, where you can go and describe ETLs, extract, transform, what's the log? No. And with Hive, you have a kind of SQL interface. Impala, some people call it the Hive on steroids. They have to go and implement it on C to make it fast. There's job scheduling. There's a tool called UCI, so you can go and, for example, if you have a workflow of data, you need to prepare the dataset B. Think of the day in the life. And you start with raw pickup files, and you want the count of queries per client. So you can go and build a workflow saying, oh, I need this data set, and to prepare this data set, you have to run this and this and this. We haven't tried UCI, but I've been told it's like rather complicated to use it. It's powerful, but rather complicated. The Apache Hadoop also include a tool called Mahout for machine learning algorithms. So clustering, k-means, regression, etc. And there's also a project from Apache called Storm for doing data streaming, because the original idea behind Hadoop was like batch processing. But now there's people actually interested in getting these analytics more or less quickly in 5-10 minutes, not willing to wait for an hour or a day. So all the social media companies, think of Facebook, Twitter, they use Hadoop on the background in order to go and classify in clusters users and offer them ads or stuff like that. And they use different combination of batch processing on a day plus data streaming for getting everything working. There are some Hadoop distribution out there, Hortonworks, Cloudera, MapR, Datamir, Pentaho, that provide commercial support. So they have administration's interface and everything. We particularly use Cloudera and works reasonably well for us, but there's some of the others, for example, Hortonworks and MapR, they have been doing some innovations around Hadoop for making it faster. So yeah, I'm not going to recommend you any, but we use Cloudera, so just a disclosure. So in the beginning, we ordered 22 servers from our provider, and what we got was that. So on your left, you will see there are 2 pallets of hard drives. So that's 240 hard drives of 2 terabytes each. And this is a table full of memory modules. So we have to go and get all the chassis, open it up, and put everything in there. It took us a reasonable amount of time. We didn't know IBM didn't actually deliver the servers built. They just deliver you the parts. So that's how we started. And you can imagine the complaints from the office people saying, what are those boxes doing there? When are you going to take care of that? And say, okay, yeah, we'll get there. But once the cluster was built, it looks like that. It's a 1 rack plus 4 servers on the side. And we have 1 router only for the cluster, 2 giga Ethernet switches with 48 ports each. So we do Ethernet bonding for each name node. The amount of, for each data node, the amount of data that moves along inside the cluster is reasonably large. The 2 name nodes in Hadoop nomenclature take care of keeping the metadata for the abstraction of the directory, the HDFS, and the data nodes keep the data in 3 copies. So that's the default. This is how we manage the cluster. You have a nice web interface where you can go and click and enable services. So on the left, you see we have 1 HDFS, MapReduce, Hive, Impala. Solar is a project for data indexing. Scoop is for interaction with database engines like Postgres or MySQL, and Zookeeper is a coordination system and the management. So you have nice graph with what's the usage, what is running, etc., and you have some audit reports you can actually provide to management. All right, that's the boring part. Why we started with the Hadoop cluster? So what was the motivation for us? We wanted at some point starting collecting data and doing analytics on and everything we have. How many of you can you give me hands collect data from your name servers? For how long? 7 days? What's the retention period? 7 days? 14? 4 years. Excellent. Thank you, Ray. All right. So before we have this storage, we use retention for 7 days. But what if you want to go back to your data and said, oh, there was an unusual event X day, and we got information from someone else saying, oh, they have also an unusual event X day. How we go back and investigate that? So we created the Hadoop cluster model or less of the idea of keeping and storing the data. And so far, you can tell we have more than a year in there. So that's roughly 6-7 terabytes of data. These are compressed pickup files from 4 name servers, which are 6 instances in total. One of the funny things you actually go and learn with Hadoop is they provide what is called partitioning. And you see the files are organized in month, day, and location. Because if you want to run a query on this data, you have to you go and find the problem. There's no way to filter. All right. So unless you have partitioning on your data, you won't have a way to give me all the data for X day. All right. And we found that the hard way. So we were storing the data just like that. And then we found, oh, can we run this query on this day? No. And actually, we ran out of resources on the cluster because it was trying to read all the files. All right, so that's one piece of advice. For reading these files, we use the pickup SERDI, which was originally implemented and maintained by RIPE. And we, well, not only, there are more than a few people actually going providing patches for keeping up and adding new features. And TCP management, V6 capabilities, etc. All right. The schema of the database looks more or less like this. I'm not going through each of the fields, but the partitioning fields are here on the end in green, and that's are the ones which allow you to run a query. Okay, give me all the addresses that send me queries when on April the 4th, 2014, for example. We also keep in the cluster some BGP table dumps once per day coming from RIPE, and that's quite a small 4 gigs. And we use that for mapping networks prefixes to ASNs, and you can do, for example, counters of how many queries we got from ASN 22474, for example. We create this aggregated data set, which are the number of queries per domain per hour, and we use that from the raw pickup files, and also is again partitioned. And we use this kind of stuff, for example, for finding what's the unique number of domain queries we got. And you can think, oh, but that's a boring one. Well, hold on, don't despair. I'll get there when we start doing some interesting stuff with that. And we use that Hive. It's a batch process that runs every day. We run a zone scan on the .NZ zone, which are proving very interesting, especially for chasing up DNSSEC deployment and the old things like open zone transfers. We have a very entertaining story with, because .NZ is organized in second level domains, so the government has a second level domain. And using the zone scan data, we prepare them with a list of these domains under the govt.nz namespace have open zone transfer. You should go and check them. And they were like scared to death. They were like really pale when we gave them the report. So the zone scan is using the DNS check tool from IIS. Thank you very much. And that one actually writes to a MySQL database. But if you try to run certain queries on a MySQL database, given the schema of that database, it kind of takes days, literally. So we imported everything using a scoop into the Hadoop cluster, and we run queries and prepare reports based on using that in no time. And then we send back the aggregates to a Postgres database where the management and marketing people can go and take a look at it. We have other data sets. We have raw bind logs from one New Zealand-based resolver, and we are actually talking to people to get more of that kind of data. So we will have the authoritative data from our name servers, and also resolver data from providers in the country. And the idea will be providing them with interesting analytics about their traffic. So for example, detecting potentially infected hosts. We also been testing another tool from the Hadoop environment called Nudge that can be used for doing web scans. So go and fetch web pages. And we can actually combine web data with DNS data and get some insights. If someone is thinking Google, please delete that thought from your mind. One of my ideas actually on this is we are exploring the DNSSEC inter-arrival query time. So I will explain a little bit more. That's really interesting. And we have we also, for example, search for bitfleet domains. So are the bitfleet potential registrations being queried on the wild. So the ability to scale on this cluster give us, for example, the possibility of calculating the Cartesian product of all the unique strings in the registry. So that generated nearly 4 terabytes of data, and once we have all the potential combinations, we can actually run I don't know, the string similarity function on those names. And you were wondering why? Because we were looking for uniqueness. So giving this domain name, we want to know how unique it is based on certain metrics. And we can actually go and tell the domain owner, you know, the domain you have is pretty unique. So maybe the value of the domain name you have is higher than you think. And we tried, so that we implemented, no, kind of, we created a wrapper around existing implementation of Yarrow Winkler, Mongi, Elkan, and Needleman Wunsch. And we want to also explore the Damerol-Levenstein distance, which is, so the Levenstein distance, maybe many of you have heard of it, but the Damerol-Levenstein adds the flipping of characters. All right. So with a cluster like this, you can go and run, put the job to run, and you forget, and then just get the data at the end of the day. So this is the point where George and Geoff, they start paying attention. And so I've been really interested around how to completely and fully detect potential validating resolvers. Using the authoritative data. All right, I love the work that George and Geoff do on the detection, but for example, we have been talking to people in New Zealand about their validation, and they do validation, but they don't show up on Geoff numbers. Why? Because they don't have eyeballs behind, they have only businesses. All right, so I was interested on providing a different hypothesis. And the idea here is a validating resolver has to go and query for the DNS key of a domain every TTL closely to the expiration of the record, more or less, assuming the signed domain that's being queried is more or less popular. All right, but we have the first and second level domains, so people querying for .nz domain names will need to get the DNS key for the .nz more or less reasonably frequently. So we went to crunch all the data from December 2013. We used the AES numbers detected by Geoff on one of his talks, the NZNOC version, which is from January. We took AES 22047, which is Chilean ISP, and we took 4 of the top NZ networks doing validation, according to Geoff. And we also took a control case of one of the providers. We actually went and talked to them and say, which are the addresses of your resolvers, and are they doing validation, yes or no? And they were doing it. So the control case, what we do is we find all the addresses sending the query and set DNS key for those ASs. We select the stream of queries, and we calculate the interval time of consecutive queries. So we order them by time. We subtract what was the difference between consecutive queries, and we prepare a graph. So the base case, this is a provider doing validation. The queries look more or less like this. So there are gray lines on vertical lines, which are multiples of the TTL of the DNS key. All right, and you see major spikes, so it's more or less flat below the TTL, but after the TTL gets really spiky, there's more activity, and a big spike exactly in the vicinity of the DNS key. All right, you might think, okay, that's more or less expected. That's what I was expecting, more or less. But then you have another spike on 2 times the TTL. And then you have another spike on 3 times the TTL. And actually this follows more or less an exponential decay up to 5 or 6 TTL, which is absolutely odd. I don't have a way to explain that now, and I will be delighted to actually talk to someone and see, oh yeah, that could make sense. So we went to what Geoff detected as validating, and they follow the same pattern, more or less. So we have the Chilean provider over there. Again, spikes around the TTL of the DNS key, and these other three are Kiwi providers. But more or less, they have the same spike on the TTL plus then a decay. This one is the only odd one, which actually gives me the pattern I was expecting. So a concentration around the TTL and then nothing else. Maybe there are more than one host behind the address. I don't know. So this is work in progress. Okay, I wanted to put out there the idea of the stuff you can actually do, mangling data. We have code available. All right, we have been writing UDF, which are user-defined functions for Hive, to do some stuff, string similarity, address family, prefix matching, which actually this is stuff that's not supported naturally in Java. You will be surprised. There were no implementation of doing that. So if you want to, I don't know, count all the traffic associated to certain prefix, there was no easy way to do that. So we actually wrote a couple of functions to do that. And the UDF delta gives you the difference between two consecutive values. So all the code have examples and explanation how to use it. It's pretty straightforward, so feel free to clone it. All right, to wrap it up, what we learned, so there's some stupid stuff in here, so mostly my mistakes. You need an extra box for monitoring. When you go and do any design for Hadoop, they will tell you, okay, you need this for this function and this for this function, but you start adding services, and every service thing is working alone. So you start having daemons piling up, and gets really messy. And also the monitoring stuff for Hadoop is kind of heavy. It's very chatty. So yeah, dedicate yourself one box for monitoring management, packages, DNS, etc., and you will be very happy. The vendor-specific management interface are really, really useful. So in a very basic Hadoop cluster, you have more than 200 configuration parameters, and you can get really, really crazy trying to dig up and finding the correlations between one and the other. And if you change this, you have to change that. So don't try it at home. If your thing is DNS, you don't want to become a Hadoop expert. The Hadoop environment is changing it's absolutely crazy how fast it's changing. So you have new version of the stuff every month. You have new tools every 2 or 3 months. And you have improvements and bug fixes very frequently. So, for example, we are using Hive 0.10, and they are already in 0.13, and soon it's going to be 0.20, so it's really crazy. Another piece of advice, the pickup 30 is kind of slow. So running queries on the raw pickup files is super, super slow. We take, for example, if we wanted to analyze 1 hour of data, it took us like 20, 25 minutes. If you export that to a text file or a binary file, it takes minute and a half. All right, so you shred a lot of time. So my recommendation is you keep the pickup file in HDFS and use any other format you may want. And also the ability of using text files or binary formats specific for Hadoop allows you to run queries on Pig or Impala. And Impala is really, really fast, so it can give you access to real data, real-time data using JBDC. All right. So the plans for the future for us is, so the cluster is going to be the core, the heart of data product we are preparing for registrars. So we're going to give them all kind of analytics. Also, we're going to start exploring classifying domain names per economic activity. So for example, in New Zealand, if I tell you New Zealand, you will think of sheep, so lamb, you will think of wine, you will think of rugby, right? So for example, how many winemakers are represented on the DNS, have active domain names? What about building companies? I don't know, stuff like that. So trying to classify by economy and then provide information to potential registrants. The other idea we are actually exploring is domain popularity based on DNS traffic and some other classifications. Okay, we have a broad number of data sets, so we are going to start the exploration sometime soon. All right, time for t-shirts. Dwayne, and we have Mehmet over there. And Geoff is queuing up to smash me in the head. Dwayne.
So looking at your graphs on, Dwayne Wessels from VeriSign, by the way. Looking at your graphs on the DNS key exponential decay, how confident are you that you're collecting all the packets that your name server receives?
Oh, pretty confident.
Okay.
Yeah, also, so we don't have that much of a volume of traffic, so we don't have any packet loss, and also the data stream is combined across all the name servers we have. So the only issue on that data set is not complete because we don't have all the 7 name servers, but the name servers we analyze, they are close to us. So they are mostly likely to send all their queries to us.
Maybe, yeah.
Yeah, maybe.
Depending on the implementation.
Exactly,
right? Okay.
yeah.
Yes, Jeff Houston. I was looking at your DNS key inference sort of thing, and I must admit I had been down that track myself about 2 years ago. And it is so difficult at the authoritative name server to understand the interactions between things that cache and hang on to the information versus the queries you see at the authoritative name server, and trying to infer from raw timing information whether something is doing some kind of DNSSEC validation and whether it's forwarding through a non-validating resolver or doing it itself. I started to rip my hair out and going, this is just madness. And in the end, used a different technique that effectively sent everyone a unique URL that was signed, so that every single time there was no cache state, which means you always saw the DNS key and DS queries if there was something going on in validation. I found the inference technique to be weak, that there were so many false signals flying around, and caches just added so much noise into this that I wasn't sure what I was seeing anymore.
Yeah, definitely. It's not a it's not a pure signal. So
on day 1, it looked like it was validating. On day 3, it looked like it wasn't, and that's just crazy.
Right.
You know, and that's why the timing sort of technique, I reckon, is just such a weak inference, unfortunately. Caching is evil when you want to do this kind of measurement.
Yeah. There was a couple of questions here from Mehmet and Martin. Okay, yeah.
Did you make any correlation between the region from where the query came and the chance that it was, that you did have a domain or domain name for this? Because this is something we have observed in our data lately, that we have certain areas where we get a lot of tries going through dictionaries or trying to find domains names, and this is very strongly regionally correlated. Do you observe something like this?
Yeah, we observe that kind of stuff from time to time, but we haven't filtered out that from here.
2 questions. So this is a pretty big infrastructure, right?
Yeah.
How much of it is actually used? Like, what is the CPU usage, more or less? And
we run a few batch jobs on a daily basis, so we have like, I will say 1 or 2 hours of major usage, and the rest is more or less idle.
Okay.
Idle.
idle or just
They are
mining
running slow.
bitcoins?
No.
All right. Okay. The other question is, so this is a heaven for law enforcement, right? But data that you collect here can be used to detect malware, detect, many other things. Do you actually currently plan to share that data, or do you have any kind of security, more like cyber security kind of approach to detect?
Yeah.
stuff?
So part of the plan of the data exploration we're gonna do is actually find odd stuff that can be related to security, and also the plan we have is to get resolver data from New Zealand providers, and part of the offering we're going to give them is actually detection of that kind of stuff. It's more oriented for our local community, but definitely we are very pro of sharing data and sharing knowledge. So you will hear from us if we have something useful. Yeah. That will be all. Okay, I will deal with you with the church after the talk. Thank you.
Hi, sorry, John
more?
here from ICANN.
I didn't see you.
Yeah, I was just wondering, have you thought about putting any of this data into HBase?
Sorry, say again? Where?
Have you thought about putting any of this data into HBase?
Oh no, we haven't explored HBase yet. I was following more or less the path from Wolfgang. But given the kind of performance we're getting and the idea of getting more real-time data, we might consider actually using HBase. And also, HBase plays really well with Apache Nudge for the web scan stuff. So it will be a better idea for merging that. All right, that's all. Thank you.
All right, thank you, Sebastian. And last we have Joe Abley.
11, yeah. You have roughly half an hour.
Good? All right. Can't actually see the screen now. Good morning. Is it a good morning? Because I have to say that some idiot decided to have a drunken pub quiz last night, and I'm not feeling very good right now. Vodka shots, I was saying. So let's see how far we can get. I've got more slides here than I have time, I think, but I'm having trouble reading anyway, so that's probably fine. So the background for this little sort of series of anecdotes is an observation that end users increasingly know nothing about the internet. We have this beautiful network that is self-documenting. We have tools that you can use to trace route and find out how things work. You can troubleshoot everything from almost every client. And then it turns out that what end users want is not any of that information, and increasingly devices where you can't troubleshoot anything because they're iPhones and iPads, and things either work or they don't. And it's not just maps and buying books or any of this sort of apparently advanced things that we did 10 years ago. Now it's much more fundamental things. It's like being able to get into your house and unlock your door. It's like getting a thermostat that actually works and heats your house so that your pipes don't freeze in Canada in February. And nobody knows how any of this stuff works. End users have no idea. I got married again in July, second time lucky. And I have a non-technical wife who will say things in the morning when I'm not properly awake, things like, Facebook's very slow today. And I will think to myself, well, you know, there's could be channel separation problems on the Wi-Fi. I've got this weird combination with DSL and cable that made sense at the time. That could be broken. The router probably hasn't been upgraded in 5 years. And Maybe it's upstream is the problem. I've got logins on some of the ISPs I use. I could probably go check. And then eventually you just realize that you just say, yes, it's right, it's slow today. So we're in this weird situation where everybody depends on the internet, but nobody knows who to call when it breaks. Because there is nobody to call most of the time. How many people have ever called Facebook and said, Facebook is slow, can you help? It's not going to work. So the only option that remains really is just to make sure things work all the time. You can't really have downtime. If you have downtime that persists for more than 3 attempts, you lose that user. And increasingly, a lot of these companies, the entire value of the company is based on the number of users that you have and the frequency with which they use the service. You can't be down. If you're down, you're dead in the water. So you have to be up. So you can do what people with lots of money or people who've had a revenue stream for a long time have done, which is to build out massive data centers on multiple continents and buy dark fiber everywhere and things like that. You can't do this if you're a startup. There's no startup that decides, okay, well, I've got I have a great idea. Let's test the market by spending $5 billion on infrastructure. That's not going to happen. So if you're a tiny startup and you want to actually get some sort of decent performance and actually test the market in a meaningful way, you have to outsource stuff. And we saw this with, I guess we can go back as far as you want. You can see this with web hosting. There was a time where you could actually run, a web server on your computer over a dial-up modem, and that would be a way that people could get your web pages. But then it made more sense to outsource that. Then we have, do you build a data center in your office, or do you rent space in somebody else's data center? Do you buy your own servers, or do you use a cloud service? So we have this whole sort of continual sort of pattern of all this sort of critical stuff, all this infrastructure that provides the service, all being outsourced. And it's compute, it's storage, it's operations. NZRS actually building their own clusters for data analysis. I think they're the odd ones out these days. Nobody does that anymore. People buy these services, they buy clusters, and they buy compute cycles, and they buy DNS. And Dyn has done very well selling DNS to people, basically along these lines. So let's focus on the DNS, because this is an OARC meeting. And I could probably just about scrape some DNS knowledge together this morning. I can't talk about anything else. So people have been using Anycast for a long time for DNS, because it seems to work. There are arguments on mailing lists about why it doesn't work, but we know the fact is it does work, at least enough of the time to make it work. Let's not argue about the architectural problems here. But we're taking this Anycast idea and we're trying to map it onto a problem space where most end users only care about particular resources being up. The end-to-end principle is a great thing. It's important. It's worth defending. But to be honest, we need to start pretending that it's broken and is dead and it doesn't exist. We can't just put resources on the internet and expect the world to be able to reach them anymore, because the internet is an increasingly broken place. Sometimes it's a temporary brokenness. Sometimes it's a persistent brokenness. It's political. It's operational. It's a reflection attack. Somewhere it's a cable cut south of the Straits of Taiwan. And if you have to be up all the time, you can depend on the internet as a concept. You can't necessarily depend on it every second of the day across the world. It doesn't necessarily give you the reliability that you need. And lots of people have noticed this. If you try and watch a movie on YouTube, chances are you're not sending your packets across an ocean. You're sending them to some spot that's very close by. You're sending to a local exchange point. You're sending them to a cache in your own ISP. Same thing with Netflix for those markets that have Netflix. I put Facebook here. That's a guess. I assume if Facebook works, they must do something similar. So if we apply this to the DNS, then what does that mean? So here's the usual example. I've arranged the map so that New Zealand is in the middle, as nature intended. Yeah, I couldn't work out last night at 3 a.m. how to switch the map upside down. So this map actually, this is the new revamped rootservers.org webpage that looks much cleaner and nicer than the old one. The old one actually looked more impressive because it had way more pins all over the place. Same number of pins though, just some of them are aggregated. So this is an example of a system that has been well anycast around the world. These are the root servers. These are the servers that your average resolver might talk to once in a blue moon. And yet this degree of reliability is important enough that people have gone ahead and deployed it. And still, there aren't that many root servers when you consider the size of the populations and the size of the user bases that depend on them. So how much Anycast do we need if the idea is to eliminate as much as possible the brokenness that occurs day to day on the internet and try and make this stuff always work? because we're providing that engine for people who need to be up. So how many nodes is enough? So the way we started looking at this is to, this is Jeff Houston's graph from Potteroo.net. So how many ASs are there? This seems like a reasonable starting point. An AS is a reasonable unit of network. There are something approaching 50,000 ASs that are advertising originating prefixes on the internet. So let's say 50,000 node Anycast network. And if we don't necessarily expect to deploy 50,000 nodes, at least we should design some architecture that makes that possible if it turns out that that's useful. There's no point in aiming for 5,000 and then realizing we needed 6,000 and now we're stuck. So let's plan to build something that's as big as the internet. So we have at least one node per AS. We're trying to keep service local. We're trying to minimize the round trip time, increase the performance and reliability. And if we're going to do this at that kind of scale, then we need a DNS endpoint, a name server, which is cheap but powerful enough. And it turns out these days, for about $2,000, you can buy a box that will, under certain circumstances, quite happily serve 800,000 queries per second without too much stress. So all these things kind of line up, and it kind of makes sense. So this is where we started to look. All right, so I think in case I missed the previous slide, I put the same thing on this slide. But one of the things I will mention is this idea of containment of attack flows on net. Lots of people have trouble with source spoof reflection attacks. It can bring down whole ISPs, it can saturate peering links, it can bring down exchange points. These are big volume attacks these days. So this is not a small advantage. The idea that an ISP, by having a traffic sink on net, instead of having mitigation devices on net, you can keep all the attack flows local. So you've got attack flows that predominantly flow from your customers to a device that's intentionally deployed as close to those customers as possible. Then you have a much smaller problem to deal with at 3 a.m. than if all your transit links are suddenly saturated and nothing works for any of your customers. So it turns out, talking to ISPs, this is actually quite a big deal. This is almost reason enough for any ISP that's experienced these attacks more than once to host a box and say, well, this is actually going to give us some performance benefit and also going to save us some support costs and headaches in the middle of the night. So if this is what we're doing, if what we're trying to do is deploy up to 50,000 boxes around the internet in other people's networks, then there are certain constraints on this because we don't have an infinite amount of people to be able to deal with things. So the whole business of receiving the box and installing it and getting it set up needs to be as simple as possible. We need to ship directly from the factory. We can't be in the business of taking delivery of boxes and opening them up and putting the special dine polish on them before we send them out again. That's a nightmare. We can't have an installation that requires someone in the data center to need to know anything in particular. People have enough work to do in the data center. They certainly don't need to read manuals and deal with complicated instructions. It needs to be very simple. And people have told us we need a box that's easy to rack. We need something that doesn't need shelves, it doesn't need rails, it doesn't draw too much power, and it's friendly on the data center. So from the security perspective, the idea of deploying a key edge of your service in other people's networks where you have no control is a little bit frightening. So, when we design these things, we have to assume that every box is deployed in a hostile network. We assume that other people have local access to it, which means they can compromise it, which means nothing we put on the file system is necessarily secret. So we can't store any secrets on the box that are not relevant to anything other than that box. We have to isolate every bit of information we try and store and make sure that the compromise of one box only affects that box and not the rest of the service. We can't have some box somewhere being taken down for operational reasons, the hard disk removed, and suddenly every other box you've got root on. That can't happen. And the other aspect to this, and we'll come to the operational bits in a second, is we expect to be able to do really cheap, frequent, regular, automatic, bare metal reinstalls. So if we have any suspicion whatsoever that this box is behaving a bit strangely, our cheapest and most immediate sort of reaction can be, well, just schedule that box for reinstall, just let it just reinstall itself. And if we can do that, then that gives us some confidence perhaps that it hasn't been meddled with, at least in the last day, if that was the last time it was reinstalled. So we have a 50,000 node edge network. We can't possibly log into these boxes and configure them by hand, so everything has to be automatic. So patch management of the operating system and the various things that run on them, the things that test things, everything needs to be automated. The style at Dine right now, the flavor of the month is Chef, for doing the sort of base automation of installations and packages and things like that. And in this case as well, Dave and Joao will talk a little later with some of their performance analysis. But our goal here is to run these things in Linux containers. And so we have a sort of a hybrid approach with Chef and Docker, if these things are familiar to anybody. Both of these things basically allow a box, once it's on net, to reconfigure itself into a completely sort of known state. So we never have the problem of one box out of the 50,000 being different to the others and causing some sort of troubleshooting problem. And element monitoring also needs to be automatic. I think pretty much everywhere I've worked before, the whole idea of element monitoring, whether it's Nagios or something more fancy, has all revolved around the fact that we have a box, something goes wrong. Was it in Nagios? Oh, we forgot to put that in Nagios, we'll put it in now. We can't do that with a 50,000 node edge network. That's not going to work at all. So the whole automatic provisioning and configuration of the box needs to be tied closely with monitoring. A box can't be accepting queries if it's not already being monitored, and none of that can be manual. It all has to be automatic. So next, not all parts of the internet, as it turns out, are created equal. It's not trivial to the end-to-end principle is not only dead in theory, but for a lot of parts of the world, it's dead in practice. We don't necessarily have the capacity or the availability to be able to have every node talk to every other node. And in particular, the paths we care about from our provisioning points to the edge nodes in the darkest, most cobwebby corners you can imagine, needs to be up. Otherwise, we can't provision service. We can't have coherent service across the edge. And then we end up with problems of problems reported in one place not correlating to tests you try and do to qualify them in another place. And that's a troubleshooting nightmare as well. So we need to be very light on the network, very tolerant of congestion, network partitions. And we think what this boils down to is basically BitTorrent or something similar. So, people have realized, even if they don't admit it in public, that BitTorrent is a very effective way of shifting large bits of data around the internet. Regardless of local conditions, it's opportunistic, it deals with congestion, it routes around it. What we've basically built here is a 50,000 node BitTorrent swarm. So if we have the problem of pushing out binary updates for packages and operating systems and provisioning data in the form of zone data, we don't necessarily have to worry about a full mesh of Notify and AXFR if we can build some other opportunistic substrate between all the boxes. So even if we can't talk from central provisioning to location A directly, maybe we can talk to location B, which can also talk to A across a local peering point, even though A's transit is down. And again, we can't configure any of this manually. This all has to be automatic. So pushing all that data out to get the service to run, the other part of that problem is pulling the analytics back. So we're having boxes monitor their neighbors as well as them being monitored somewhere else. We're having packet capture on a local host, generating amounts of data that can never be centralized because we don't have the capacity to do that. But we can push out rules for summarization and remote interrogation of the data and then pull the results of that interrogation back, again, over the same active substrate that connects all these things in a non-direct fashion. So this, in principle, seems to work. This is where we're going. So we have these boxes. The test boxes, or the sort of early stage deployment boxes we have, is 64 gigs of RAM. They have, I forget how much CPU, enough, I suppose. They're fairly capable servers. But part of the point here is if we've got sort of 50,000 different places where we can run things, we want things to be agile. We want to be able to respond quickly to the idea that we want this particular service to be live in Buenos Aires because we've got a particular reason why that's important, and we want to be able to push that up quickly. So again, at that scale, we can't go around and pre-qualify and test with human eyes and make sure it's safe to bring up that service in that place. We have to have a base assumption that it's always safe to bring up a service, or at least to ask for it to be brought up. And that means we need to protect the resources of the box and the other tenants of the box from whatever new thing is arriving on the platform. So our main concern, the main constraints we have in this edge platform is RAM. 64 gigs sounds like a lot, but you don't need an awful lot of big zones before suddenly that starts to look a little bit creaky. And the last thing we want is a zone just to pass that extra bit of growth and grow this a little bit too big, so we start swapping, and that causes the entire box to collapse and every service stops working. So we need to constrain them. So our approach for that is to use containers to reduce the maximum amount of CPU and RAM available to any particular tenant, and make sure that that tenant can't step on another tenant that's on the same box. So when we design that, we can still ask for a big container to be brought up on a box that's already quite full. That's fine. We can ask as much as we want. If it doesn't work, we'll just get the telemetry back saying, no, that container didn't come up. But we'll never be in the situation where we bring it up and everything else in the box starts swapping madly. So then the question comes, we've got a 50,000 node edge network. If we have a 5-node Anycast network and we start to sync an attack in a particular place, then we, as humans, we can look at it and say, well, what's the right thing to do here? We could withdraw the service prefix and have the traffic reroute somewhere else. That's got a penalty. There's some period of time where the prefix is going to flap across the global internet and be a little bit unstable, but maybe that's okay in this case. Maybe that's the best answer. In other cases, that's not the best answer. If we are syncing an attack in a particular ISP, and that's where all the traffic is going, and all the traffic is coming from their customers, then syncing it in that ISP is the best place to sync it, even if it hurts performance for those customers. We're protecting the rest of the world by syncing the traffic and isolating it. So we want to be able to do one of those things. We really want humans to be able to sort of interrogate the situation and find out what's going on and make a reasoned decision. But again, it depends on the frequency of events. So we expect to have to do this with automation. Rise of the NetOps robot army. But we don't know how successful that's going to be. This is going to be a learning exercise. This is the kind of thing where we're going to automate things as it makes sense, as we gain experience with actual attacks. But there's going to be humans involved to start with. And there will always be humans involved somewhere, I suppose, even if we're just robot slaves. So putting it all together, what we're trying to build is a DNS service that's distributed on a scale that we don't think has been done before, or at least none of us who are doing it have seen it happen before. The idea is to add performance, is to work on an internet where the end-to-end principle is not available, doesn't work, where we can't reach certain nodes, and we're providing pockets of service that together add up to a global service that hopefully is better than what we could do with a centralized model. And as a side effect of this, building out into lots of different networks means we get lots of views of local locations. So this is a platform that we can use for active measurement, for routing table collection. We can do it for client reputation. We can do sort of GeoIP type applications. So there are a lot of significant things that come along with having this sort of global footprint. But obviously the main feature, or the main focus is to actually provide the service rather than the ancillary benefits. So where are we with this? So of our 50,000, 20. It sounds quite pathetic when you talk about 50,000, but we've got to start somewhere. So it turns out that Dyn has, well, it doesn't turn out, we know because we work there, but Dyn has 20 data center locations. So these are not the kinds of places where we're planning to put these small nodes, but it seems like a good staging point to start from because we are the ISP in those cases and we can troubleshoot both ends of the entire thing and make sure it all works. And that will give us some baseline performance as well. And suppose, you know, the first person who's interested in hosting a Hivecast box is somebody who is in a tiny ISP somewhere remote. We don't want the internet's global traffic for twitter.com to flow down to that tiny island. So the 20 nodes in data centers where we have paid transit gives us a baseline performance upon which we can build. And so you can see the initial deployment beyond that as optimizing, providing local optimization for people beyond the baseline 20 data center locations. And then after a certain point, you know, the data centers will become less important because the bulk of the traffic will be answered elsewhere and on one or more of these small footprint boxes that we deployed in ISPs. So this is starting now. And then the next phase, we're thinking of, well, we're planning on sort of sprints of 200 boxes being pushed out into ISPs starting in Q3. And locations prioritized by customer demand. So again, we think this is something that will benefit the ISPs, but we also think it's going to take time for that benefit to become apparent. So word of mouth is a good way of starting boxes, starting the process of finding locations to put boxes. And then after that, we sort of have a whole bunch of partnerships that we intend to build on to try and push these boxes out in lots of other places. So that's that's it, I think. That's the last slide. So this has been what feels like an over-markety presentation. Hopefully there was at least some technical content, and I'm, to be honest, just looking forward to going to bed at this point. I think we have a few minutes for questions. No, sprint as in agile effort, unit of work, nothing to do with actual 1, 2, 3, 9. Although if there's anybody from Sprint who wants boxes, then we should talk.
So Warren with Google. Hey.
Hey, that light's very bright.
Yeah, I know.
Yeah.
I figured it was.
Yeah.
So are you planning on having like a separate subnet per tenant, or is this sort of one large set of IPs that everybody uses?
So it depends. It depends on the tenant. Our basic unit of work on the edge is a container which does stuff, and that container has an interface to the rest of the box, which is basically a well-known API at the edge, which does things like health checking, and all the provisioning of pushing all the stuff out is, as well as the set of health checks that correspond to this container so that we can tell that it's working. It's also instructions for the routing subsystem on the box to be able to announce prefixes. So these things are all tied together. So you could imagine, for example, for a TLD that we were hosting, they might well have /24 and a /48 from their local RAR under some critical infrastructure policy, and they will bring those addresses with them, and we will tie those routes to that container. And that mapping is quite simple. And then, as you correctly inferred, there are other situations where we don't have exactly one address out of a /48 that's in use. So therefore, we have some degree of shared fate between different services that are all tied to the same prefix in the routing table. Oops. So in those cases, in some instances, if we're hosting a large number of zones on a single name server process, we still kind of have one point to measure, one way of deciding to withdraw a route or advertising a route. In other cases, we need to do a bit of tunneling or some other way to try and fill in where we have a service that goes down without flapping too much for the service prefixes. So you're right, it's not as simple as it sounds, but it's not that complicated either.
Hi Joe, John here from ICANN.
Hi.
I was just wondering, have you thought about how you're going to visualize 50,000 nodes?
How are we going to visualize them?
Yeah, or are you not going to bother?
We intend to go to space and look down. I have not yet thought, I don't think any of us have thought, how we fit all these things on one page in a map, because it's just going to be filled with pins. We can almost forget the map. So, so I don't know. We don't have 50,000 nodes today. We don't expect to have 50,000 nodes in Q3. So this is a problem we have time to deal with. But you're right. How to fit that many pixels on a screen? We might need to buy some bigger screens.
And also, have you considered opening up your recipes for configuring all of this? I mean, you're solving problems that a lot of us are also solving. So I was wondering if you would be able to sort of put your chef recipes on GitHub or something.
Oh, I can certainly take that back. I don't think it's anything we've talked about. I mean, we certainly have lots of other things that we throw on GitHub and publish the code for. Yeah, it's a good question. I'll find out.
Lars Lehmann from NetNode. There's one aspect that I didn't hear you talk about, which is something that we struggle with, which is the negotiation of the peering arrangements. You have like 50,000 peering arrangements at least that you'll have to look into, which also includes when you add on these new prefixes and filtering and all that. Do you have any thoughts about how to handle that?
Well, we made a start along trying to minimize the cost of that. I mean, years ago, I worked at ISC, and ISC had a strong mandate to support exchange points. And FRoot nodes were, I think, almost exclusively deployed at exchange points. And all the ticket queues in which people would request peering and point out that things were down were largely at one point cleared by me. So I had a certain appreciation for the amount of pain involved in that, and really how easy it is to do a bad job. And there are a lot of people who take peering very seriously, and if you are down at an exchange point and are not responding to tickets saying this session is down, we need it back up in a reasonable time, that people are going to stop peering with you. And peering is expensive. I guess that's the basic summary. So sometime after I was working at ISC, I was working at ICANN. And I apologize to John for the mess that I no doubt left him to clean up. But at LRoot, we took a different approach. We deployed into ISPs rather than, in general, at exchange points, specifically for this reason. So what we're basically doing is distributing the cost of peering to the ISPs that host the boxes. Now, at Dyn, I don't know that we've got that far in our planning, and we have more resources at Dyn, more than we had in the DNS operations department at ICANN. So I think there'll be a hybrid approach. There'll be some peering. There'll be a lot of boxes in provider networks, and we'll manage the both. But you're right. I mean, the cost of peering is not to be underestimated. The idea I can just pay this much for a port and suddenly I have access to all these ISPs sounds fantastic in theory, but in practice is a bit more expensive.
But even so, even if you deploy under ISPs, you still have that single BGP session that needs to be set up and dealt with.
That's right, yeah. And that's part of the process I described as being automated. So when you receive the box as an ISP and you go to the web page and say, here are my details, you get a custom image you can use to install that box, which is pre-configured.
Okay, I get it. Thanks.
Yeah.
So Joe, are you building out for the grand future of TLS over TCP?
Well, I don't know. We could argue about the stability of TCP over Anycast.
I'm not worried by that.
You're not?
I'm just wondering if the box size you've chosen and your query rate per second in UDP is going to fit comfortably in a brand world of held sessions on a kernel.
Well, there may well be situations where we have a challenge, but fortunately we have a scaling option there that can take care of it, because if we're able to deploy a box pretty much in as much time as it takes it to ship from Supermicro, then we can get rid of those scaling problems, even aside from traffic engineering, by just sending out more boxes. So if one box is not enough, if that looks like it's half full, and half full is the threshold of nervousness that we have about capacity on the box, then we can send another box. Or we can send a box to a neighboring ISP, or we can say that this particular node seems to be attracting a lot of queries from ASXXX. Let's go talk to them and about what traffic we see and how we could keep that traffic local in the network. And again, we divide the traffic load. So I think we have options there, but yeah, you're right. I mean, you can never predict exactly where you need capacity. You just hope that you can deploy fast enough to keep ahead of the curve.
Antoine Schuren. Joe, one of the assumptions you make in your model is that all ASs are alike. And we're trying to get some sort of a configuration parameters for Anycast networks. And I've done some measurements recently, and where I see that there's a large increase in large networks, especially content delivery networks, where you cannot say that being on the AS means that the quality improves, because there's a difference on where you are in the network, and you cannot look into the network from your point of view. So how do you think you handle that?
No, for sure. The 50,000 node network, because there are 50,000 ASs, is a flip indication of scale. I'm not suggesting that every AS is the same. So the place where we see most of our client traffic comes from, resolvers for the traffic we actually like, and from infected Windows boxes, sorry, for the traffic we don't like. So, I mean, the goal here really is to go into the eyeball networks where the performance actually matters to the end users. Going into a hosting network, depending on the kind of hosting, although a lot of VPS boxes that are used by our new and upcoming shoestring competitors are also sources of lots of traffic, which is worth syncing. The other distinction we can make is a small ISP whose infrastructure is largely centralized in one point. An example from my neck of the woods is a lot of ISPs in central Canada pretty much entirely exist in 151 Front Street in Toronto. So that's a good place to be, and that's where we could put our boxes. Another network might span 3 continents, in which case putting a box in one place doesn't do anything for people 2 oceans away. And we need to actually work with as partners with those networks and make sure we put the boxes in the right places.
What makes you think they will partner with you?
Well, we don't know until we try. The answer is always no until you ask.
Yeah, because they're anycasting their resolves as well, right?
Most of them are, I think. Yeah. Many of them are.
So, a few questions. And I work very closely with Joe and Dave, obviously, in L, and it's finally good to see what we have, cored up there is being used in an infrastructure that really matters to end users. I mean, as you said earlier, queries to root servers are, almost rare because of the cache and all that. So kudos for that. This is an idea actually that has developed over many years and used by several others. Kudos to those people as well, all CZNet guys, Elro team and ISC guys, obviously. Why ship physical boxes?
Well, part of the answer will no doubt.
Before you answer, can I ask one question to the crowd? Sorry. Who here in the room has production virtual infrastructure in their premises? So, now the question.
Thank you. So your question was, just to remind me, why aren't we using VMs? Why are we shipping physical boxes?
Why do you need physical infrastructure?
The reason we want physical infrastructure is because we want certainty on the resource constraints of an individual node on the edge. Because we expect there to be resource contention. We have to have a budget that we can carefully allocate to particular containers that are doing particular stuff, and know that the capacity is there, and know that the size of the VM, or the size of the environment, is not shifting from underneath us. So that's one reason. And the second reason, as I was about to say before you so rudely interrupted, is that Dave and Joao, a little later on, will talk about some performance characteristics based on measurements that they've done. And I won't pre-announce exactly what the results are, but we like containers. Yeah.
My personal recent experience, if we are trying to stay away from cloud, it doesn't scale. And we will see that over time, I guess, not overnight.
That sounds like a challenge.
Hi, I'm Matt Weinberg from VeriSign. You have 200 units that you want to deploy in Q3. That's less than half of 1%. What are your realistic goals for penetration into the market and timelines associated with it?
Well, I think really this is a process of exploration. Until we've deployed a certain number of boxes, we don't know the conditions, and we don't know where we need to fill in. We have a certain amount of data from the nodes that we do have, that we currently run in data center style edge deployments, but we don't know exactly what we need elsewhere. We basically don't know how bad the end user experience is right now with the large number of, well, for us, large number of data center locations compared to how much better we can make it. So the 50,000 idea is not a target. The idea there was we shouldn't design anything that we're going to run out of capacity on or is going to become too big to handle. So we should start thinking big from day one. We don't necessarily ever expect to have 50,000 nodes deployed, but we should be ready to have 50,000 nodes deployed. That was the approach. So 200 nodes being some small fraction of 50,000 doesn't necessarily seem that relevant. The immediate thing is let's put those boxes in different places and find out what kind of impact they have. And I should probably add there that, when I say what impact they have, we're not just relying on passive captures and active measurement between boxes and things like that. It so happens that we have a lot of customers who have quite developed analytics at higher levels in the stack who can tell us exactly how the performance changes over time. So we have some means of actually measuring this stuff and adapting. Is it time for coffee yet?
All right. Any more questions? Then I think it's time for coffee, and be back at 11:30, please.
Right. Thank you.
Are you trying to sell the service, or do you want to buy a service from them, or is it a cooperation once you know a little bit more, or trying to look for partner, at least in Germany, we can give you also something on this small RFPs for running the operations for
Yeah. Yes.
All right, welcome back from the break. First session is DNSSEC deployment in China by Chi. Come on up.
Hello, everyone. My name is Zhao Qi. I'm from CNIC. Very glad to have the opportunity to share the experience of DNSSEC deployment in CN. I hope this presentation will give you some useful information. Before starting, I want to thank Mr. William, the first speaker. He opened my slide at the beginning of his lecture, so we have the chance to see this page twice. Okay. Okay, let's start. This is the main contents of my lecture. It mainly includes 4 aspects. The first is overview. I want to introduce a brief I want to give you a brief introduce about the whole progress, and it will give you a general impression. And the second part is preparations. I want to introduce my prepare works before the deployment. And the third is deployment. I want to introduce 3 steps of our deployment. And the end part, the last part is monitoring and observations. I want to introduce the change after DNSSEC deployment in CN. And at the end, I want to give a brief analysis about a small size DDoS attack happened recently. Okay, this slide shows the status about DNSSEC deployment around the world. I'm so sorry, maybe this is not the latest version of my slide, but as I know, there's already 571 TLDs in root zone in total, and 385 TLDs are signed. 375 TLDs have trust anchor published as DS record in root, and 5 of them also have trust anchor published in ASC DLV repository for backup. I'm very glad to say that .cn is one of the signed zones from the end of August 2013, finally. And we finished the DS record submitting in November. That was the most exciting things for us in last year. Okay, let's overview our progress. It is well known that the whole progress of the DNSSEC deployment has been divided into 5 stages. And the first stage is experimental. The task in this stage will be doing experiments in the test bed. We have finished this stage from December 2010 to March 2013, and it took over about 800 days. We carry out a detailed test about the situation which may be occur in the future and develop solutions. That was the cornerstone of our deployment. And the second stage is announced. You can announce the approximate time point of further work. We have announced our schedule on ICANN 46 public meeting in April. And we still conduct training and drills in this stage. And the third stage is partial. And the work of zone signing has been finished in this stage, but the DS record of your zone has not been submitted to parent domain. We have finished CN and Zhongguo, the IDN of .cn in the end of July, and put them online by the end of August. Okay, the fourth stage is DS in root. In this stage, you should submit a DS record to your parent domain, so the trust chain has been established. We have finished that for both CN and Zhongguo in November, and they both work well. And the last stage is operational. You should be able to receive DS record of your child domain. And we are going to develop and upgrade the system like DB, SRS, and WHOIS, and so on, and then put them online. We are still in this stage now. Okay, this slide shows the key information about used in CN, and the table 1 shows the key algorithm and key length and key type. We followed the suggestion of IFC 4641, and which is now obsolete by IFC 6781, that both ZSK and KSK use RSA SHA-256 algorithm, and the length of ZSK is 1024, and the length of KSK is 2048. We use NSEC3 to avoid the traversal attack. And the table 2 shows the key row cycle and the RC period. The row cycle of ZSK is 90 days, and the row cycle of KSK is 12 months. The RC period in the zone is 30 days. And the right picture shows the key rollover mechanism. The rollover policy for ZSK is pre-published, and for KSK is double signature. This slide shows some key pair management and private key protection. We design a complex management strategy that all pairs of keys are generated in HSM. And 5 key administrator accounts are generated during the HSM initialization progress. Only more than half of them have passed identity authentications can get across. And for private key protection, we divide all the encrypted keys are divided into 5 segments. And they are all stored in the independent smart card, and each of them is kept by a key administrator. And in emergency case, they can be restored by using any 3 segments. Because the DNSSEC operation needs a high-level security, so we put our hardware device into a physical strictly protected physical environment, which passed the C-level Army security standards of PRC. And only authority person may get across. Authorized. HSM and hidden master servers are kept in an electromagnetic shielding data center, and a backup system is established in a disaster data center in Chengdu with the same security insurance level that of Beijing. Okay, the second part is preparations. The first job I want to introduce is Smart DNSSEC, an independent research and develop software. It took us about 1.5 years. The purpose of Smart DNSSEC is to achieve automated development of DNSSEC. It can resolve the key rotation problems. It has saved lots of manual operations during the whole development progress. So it's a reliability and scalability software. The second job for preparations is internal simulation test. We establish a closed-loop simulation environment with root, TLD, SLD, recursive, and so on, and the service of SRS, WHOIS, and of course resolving is covered. We use 5,600,000 names in .cn to simulate the production environment, and 6,900,000 times of SRS update has been performed. 170,000 DS records has been submitted by SFD. We have finished 102 times ZSK rotation and 51 times KSK rotation. More than 20 bugs of smart DNSSEC were fixed. And the third job for preparations is an open test. We organize an open test with main ISPs in China, include China Telecom, Unicom Mobile, CST-NET, Threenet, and so on. The result is that on backbone, about 0.28% can't support UDP packet size larger than 512 bytes, 3.41% with UDP packet size limitation policy. So all of this could be fixed by TCP protocol. On user side, which with multiple access type, the result is that 0.057% DNSSEC query are failure. All of the failures were caused by network packet loss or latency. It's not by DNSSEC. And we use the method is dig plus DNSSEC option. And the protocol EDN0 and TCP is also being tested. The conclusion is that the internet environment in China could support DNSSEC. So based on that result, we have the confidence to take the next step. The last work for preparations is platform upgrading. The rhythm number for keys are generated by industrial certified vendor for high quality. And because DNSSEC brings us larger packet size and zone size, so we upgrade our system memory from 16 gigabytes to 32 gigabytes. We also upgrade our network equipment like router, switch, and firewall to support UDP packet size larger than 512 bytes. The bandwidth of our node side of around the world also has been increased to face the increased length of data packet. The third part is deployment. The first stage for deployment is zone signing. We have established an independent hidden master system for DNSSEC. It includes hidden master, hidden slave, and choose part of the servers in all the nodes to ensure the continuity of online service. And CN Zhongguo and 43 SLD and .cn are signed by HSM cluster, which are dual active for speed up signing and add on the service redundancy. It took less than 20 minutes by signing 10 million names in CN, and DNS service is still online for resolving, and the DNSSEC service is offline for trial operation. So in this stage, DNSSEC service is transparent to the user. And the second job for development is DNSSEC service online. It took us about 4 months. We design detailed switching and rollback schemes that DNSSEC service are proceeding online node by node and step by step. include switching, validation, analysis, and then the next node. We establish a backup system with 2 levels to ensure the continuity of resolving service. It includes DNSSEC AXFR system and the DNS AXFR system. A faster switching mechanism through centralized management should be used when there's any error occurs, and it will be done within 5 minutes. And in this stage, the user can get DNSSEC reply when he send queries to our node. The last job for development is DS submitting. We generate DS record for CN and Zhongguo in HSM, and we have passed IANA's validation smoothly. Both DS record for CN and Zhongguo are becomes effective in November. For validation, for DNSSEC service validation, we establish a recursive platform with which turn on DNSSEC option and performs periodic validations. We have finished 2 times of ZSK rotation, and will face the first time of KSK rotation in this year. I think that that is much more important than ZSK because DS record in the root zone will be changed. That was a challenge for us because it was the first time. The last part is monitoring and observations. This slide shows our monitoring system. We establish a monitoring system with 2 levels, and level 2 is alarm. The purpose of this level is to report faults exist in the system by wired area network DNSSEC validation, key synchronization, SOA comparison, log checking, VIP domain checking, and so on. The other level is warning. The purpose of this level is to call attention to some important things that will be coming soon, like key rolling event, DS event, key regeneration, and so on. This slide shows the real change after DNSSEC deployment. As we know, DNSSEC brings us larger packet size and zoom size, so we use OPT-out to reduce the increase of zone size at the beginning of the DNSSEC deployment. It is shown that in picture 1, it only increased 50 megabytes in total. But there is already RSIG in the zone file, so the packet size reached about 2.5 times larger than usual. But why? We have analysis the real traffic in CN that it shows there is already 68% DNSSEC query in Euro. So we can deduce that after SLD and the recursive name server have finished the DNSSEC deployment, the bandwidth cost will become larger. But why there is so much DNSSEC query in Euro? Because as I know, the most recursive server in China has not turned on DNSSEC validation. So maybe we have we need further research. And this slide shows the query type in .cn. For DNS query flag, -ADC, -AD, and hyphen are the top 3 for all. They accounted for about 96%. And for DNSSEC proportion, as shown in last slide, there is already 68% queries with DNSSEC. So based on a simple estimate, the packet size of .cn will increase to 542 bytes at least after recursive and SOD turn on DNSSEC. Oh, I'm also doubt about the proportion of -AD. It almost reached 1/3 of the total queries. Why there's so many DNS queries without C flags to an authority name server? It really makes me confused. And we must note that the results are the same in China and abroad. So we deduce that maybe it was caused by the feature of recursive name server software. Okay, and this is the last slide for this presentation. It shows a small size DDoS attack happened recently in CN, and the QPS reach about 2.4 times larger, and the packet size increased to 700 bytes average. So the bandwidth reach about 4 times larger than Euro. So it shows that when after recursive and SOD have finished the DNSSEC deployment, the DDoS attack will make much more threat to CN. So there is 3 challenges that we must face. How to push SOD Open DNSSEC, and how to push recursive Open DNSSEC, and how to face the pressure after 1 and 2. Maybe we need much more work to do. Okay, that's all for my lecture. Any question or comments?
Hi, Dwayne Wessels from VeriSign. Can you say why you use double signing for KSK rollover?
Yes, I think it's easier for KSK because we have the S record in the root, so it's if we use the ASK for if we use pre-published for KSK, maybe the zone size will become much larger. So we use double signature.
Okay, thanks.
Matthijs Mekking, Anonymous Labs. I was wondering, why did you make your own DNSSEC software and not go for existing software?
Okay, the software you means smart DNSSEC. He can automatic finish the key rotation or some other management job. So I think that will speed up our job, maybe make our operation more easier. So maybe that is the purpose.
Okay, so you missed that feature in existing software.
Yes, maybe.
Okay, thank you.
I actually prepared a question in Chinese, but I'm not going to ask in Chinese. DNSSEC in general in China, with the extensive firewalls being in place, did you see any non-expected behavior because of that? After signing of these many domains when they were in production?
On our side, the queries are not are always normal as we monitoring. So maybe there's not very much change on our side.
How about in general within the recursive side when the domains are validating?
At least no, there's no much recursive company to reflect the errors after we have performed the DNSSEC. So maybe they don't turn on their sec validation on their software. Maybe.
I know CNNIC is very active in China, and you guys are pioneer in so many different things. Do you also have plans to talk with ISPs about enabling validation in country?
Yes, but maybe that was not determined by us. We have the passion to do that things. Maybe we can try.
Anton Schuren. Well, I saw that you investigated the Chinese networks for at least for the packet size.
Yes.
I remember that when I was in Beijing for the ITF back in 2010, when I was not on the ITF network, all the DS records were stripped from my answers. Is that still happening? Because otherwise you couldn't validate on those local networks, right?
Sorry, I don't follow you.
Okay. I saw it when I was on Chinese networks in Beijing that DS response for DS records were stripped from the answers.
From where?
For firewalls in hotel networks and things like that. So
maybe that is not our problem.
No,
so,
of course. But have you investigated that? Because otherwise your effort has not been.
So I do not know very much details about it. So
Okay.
sorry for the.
Any other questions? Okay. Thank you, Chi.
Thank you. Thank you for your time.
Next, we have DNSSEC audit framework. With
Hello, Matthijs from Nanonet Labs. We do NSD, Unbound. We do other stuff as well. For example, we did this DNSSEC audit framework. We published it in a couple of months ago. I'm going to talk you through it. So, background was we collaborated with Switch on this. They want a second opinion. Who are you going to go through if you want to audit on DNSSEC? Most people who have DNSSEC knowledge are not really auditors, at least not in my world. Certainly, Nanonet Labs has no experience in being auditor, so if we wanted to do that, we had to go through the whole exercise of how to do a structured review of such an infrastructure. If we were going to do that, of course, we won't do that one time. We want to make something that we can reuse and others can use. So that's the whole idea of this framework. There are a lot of DNSSEC documents that go about DNSSEC, but doesn't really cover auditing. We have the operational practices RC in the ITF. We have stuff that talks about how to write your policy on DNSSEC and your practice statements. We have deployment guides, but no auditing guides. We do have audit documentation, but they generally don't talk about DNSSEC. So combining them, you get a framework what you have to do when you want to do such a review. It's a framework everyone can use. It's an attractive license, I guess. It's targeted at TLD operators, but I think it's really useful for any kind of person or organization that runs an authoritative name server. The audit actions in the document might be a little bit high level for other DNSSEC operators, but that's not the issue. You can, if you think this does not apply to me, you can still make use of the other topics. These documents we use as the input. 6841 RFC, which is the DPS, is taken as a scope. It actually covers all the topics you are interested in, you should be interested in if you deploy DNSSEC. So yeah, it makes sense to take that as a scope. 6781 is the good practices. If we don't know what will be the good default, we'll take this document and then the same defaults, we use them as the default as the values. Additional practices we took from a NIST document, and for auditing guidelines, we very loosely base that on ISO 27008. Requirements, we use the old good-fashioned must and should from RC 2190. This is a little bit of how a audit action would look like in the document. We have an objective. We want to achieve a certain goal. That's the objective. The control is how you would able to achieve that objective. And then the practice will guide you to how to implement that control. And then the actual audit actions is to check whether the practice has been correctly implemented in your infrastructure. How you do that, we identified 3 different types of actions. You can do the interviews with the responsible persons in the organizations. You can do the examination yourself, for example, looking at documentation, looking at answers from DNS queries, and you could do tests. For example, this is a shortened version of one of the actions from the document. One thing is to check whether the organization has a policy and practice statement. What the objective of that is to gain a shared understanding of all the stakeholders who make use and who operate the DNSSEC service in their organization. How do you achieve that people can read that? Well, make it publicly available, and implementation would be put it on your website. What should it cover? It should cover all the topics outlined in the DPS, of course. Very straightforward, but just putting all those actions into a document makes it very easy for a guy who pretends to be an auditor to follow that outline. These are all the topics we cover in the framework. Yeah. If you want detailed information about that, I suggest you go to the document. I put a link in the slides on the last page. The other controls is actually just a brain dump of all the things we could have done, but really didn't due to lack of time. So more examples. What could be or questions you can do in the audit of a DNSSEC? Do you deploy NSEC or NSEC3? There's no good. There's no bad answer here. Both are good. The whole idea is to trigger the organization to give you the managerial decision of why someone implemented NSEC or NSEC3. Same for accepting DNS key or DSS. Why don't you accept DNS key? Why don't you accept DSS? Rollovers. So yeah, just for all the issues, I want to make very clear there's no bad, you didn't do this action in the audit. It's try to figuring out why the organization made certain decisions. So yeah, Pirates of the Caribbean style, this will be the motto. To summarize, work of Switch and Nelnet Labs, it's a framework you can use, you can edit, you can go to a third party and say, can you do this for me? I got a great framework, can you do a trial? If you're going to do that, we would really like your feedback. We did the trial at Switch with this framework. Both parties were I think very pleased with that, but I think it needs more runs on other operations. And then please come back to us and say why it was sucky or not. Questions?
Hi, it's Joe Abley here. So this is a pretty naive question, but I've been paging through this document and it looks great, but I can't tell whether the goal here is to provide a way to review someone's architecture and the decisions they made in deploying DNSSEC, or whether the idea is to provide a framework so someone can actually audit them in the sense that we want to be able to make sure you're following the procedures you said you would follow. Or is it both?
If I'm getting the question right, it's a very good question, because one thing you're talking about is am I doing the DNSSEC correctly? And the other thing is, am I compliant with my own policies? It's more of the first, because if there's a missing policy document, then you cannot do that, and then you need something else, some other reference. But the whole idea is to give guidance for an auditor or pretend to be auditor to follow these lines to do an actual audit. And then it would not be a compliance audit with your existing policy documents.
So I'll just add that I think this is actually really useful, and I think your introduction of the question that you were asked and the reason why you made this is a good one, because other people have been saying for years we've deployed DNSSEC, including a bunch of us who signed the root, and apart from asking everybody in the world to give comments and then receiving no feedback, you've no real way of measuring whether your design is any good. So it's great to have a checklist.
Thanks.
So I kind of know your answers to this question, but I want to see what others also will be thinking. This is a great framework you are putting together. Is NLNet Labs planning to offer some sort of monitoring service for those who are signing? And I know your answer, but maybe someone in the room wants to do that. But what is the answer?
I think if someone is doing that, I don't care about the entity. I think it's very good and useful that you're using this framework to put on new services and use this as a basis. Yeah, I would really applaud that.
Are you aware of anyone actually doing it?
No, I'm actually not aware of many people who have looked at the framework or try to use it, and that's why I try to get the sense of the room if people did that, and if so, please provide feedback. So maybe it's a good question. Anyone knew about this already? Not that many.
One other question up here.
Shane Kerr from Dyn. So Holland, does it have a government mandate for government offices to use DNSSEC?
I think that's in the making, but maybe you know more about that?
Like some sort of apply or explain type policy? Okay. Okay. So is there any idea to kind of reach out and maybe make this a resource available to the Dutch government or maybe even other governments?
That's maybe a good idea, yeah.
Okay. Okay. Cool.
All right. Any other questions? No? Thank you.
Thanks.
And it's now close enough to lunchtime. Sebastian will be doing PGP key exchanges from 1:15 to 1:40.
Well, we're trailing very well on the time. We are 25 minutes ahead of schedule, yay. One of the promises of the program committee before the meeting was giving slots for lightning talks, and we totally missed that. So we want to amend our error. We're thinking giving 15 to 20 minutes for lightning talks. So I know Warren was interested in one slot. if anyone else is interested on poll. So I can give you 5 to 10 minutes each, depending on your interest. So if you have anything to present, send it to me so I can upload it, and that will be on the last session of today. So immediately after the coffee break. All right. Don't worry, we're going to finish on time. Everything is tracking pretty well. So if anyone else is interested on a lightning talk slot, let me know. With no any further comments, we have lunchtime. The key signing is gonna be, well, we are more or less 20, so it should be upstairs outside the restaurant. And I'm going to prepare the material. So if you want to send your keys, do it now, because I have to go and do the printouts. All right, thank you. What time? Oh, the same time. I think it's at 20 past, no, 1:40. Yeah. Yeah. So we're starting 1:40 lunch, long lunch break.